All right. Hello. This is my final semester reflection, and I've included all parts one, two, three, and four in this little presentation I made. And I'm just gonna voice over it to cover everything I need to. Okay. So for part one, that's the identification and definition of the problem. So here's what I have. Okay. So the problem we were facing is to irrigate the prairie in our school using rainwater and off-grid power systems. And for the design process, the first step we had to do was empathize, and we started to ask Ms. Steinhammer questions that we can use to narrow down our goals. So here are some of the constraints we came up with after talking to Ms. Steinhammer and empathizing with her and finding out exactly what the problem was. So we needed to use rainwater to irrigate the prairie with backup when necessary. And this introduces the need for a rainwater collection system. And again, this has its own issues that we have to deal with. Like, for example, it cannot disrupt natural runoff and it cannot flood the building. I'll get more into detail. I'll get into this more detail in just a little bit, but this is just an overview and definition of the problem. And next, we have to use solar energy or some type of off-grid energy as much as possible, and we need to have backup power when needed. We also know that all the plants growing in the prairie are native to Texas, which means that they don't require too much water, but they still need controlled water flow on demand. It needs to be automated, obviously, and a cistern has already been put in place to aid with water storage. So this means that we already have water storage and we don't need to worry about that for this project. And last but not least, we also have a hydroponics system that needs to be installed, which we already have all the materials for. It's just the implementation. So it's like a little side project along with this. Okay, so here's a picture of the garden, and this left side of the patch is what we're irrigating. So that's native to Texas plants all over here, and it's approximately a little over 2,000 square feet of land that we need to irrigate. And this roof over here, that's where most of the rainfall we need is going to be coming from, because this roof has its main downspout leading to just near this pathway that leads into the building. So now that we clearly identified the problem, let's look at how we distributed teams and project and look at some project parameters. So when we first started with this project, because of some of the experience I had from last year and my ability to like lead, I was assigned as one of the systems integrator. And so we split the classroom into four separate groups. So one group is working on hydroponics, one group is working on water collection, one group is working on off-grid, and one group is working on irrigation. It's important to note that hydroponics already has most of their work done. So members of the hydroponics group are mostly part of, or like scattered across the other three categories. But when we do need to do hydroponics work, like for example, when we had to do the glue ups for the plywood, we all got together and worked on that. So next, part two and part three, I'm gonna provide justification of the problem. So why is it important that we need to do this, and some of the design goals, parameters, and constraints that we have. So due to industrialization and like large scale agriculture, a lot of the native to Texas prairies have been used up, and today only 1% remains from before Texas was like colonized, and we want to preserve like that history and prairie from as part of our school. So reintroducing the plants will take some maintenance from our side before they start to just sustain themselves again. And harvesting our own water, because we're focusing on this like theme of sustainability and protecting like native to Texas plants and saving the environment and stuff. Harvesting our own water is more sustainable and will be cheaper in the long run. We want to use as little city water as possible. Manually watering plants is not sustainable or consistent, because most people, again, they'll be busy doing their own work as a teacher or a student, and we cannot hire like a designated like gardener or someone who just waters the prairie. That is just outside our scope. But with an automated like irrigation system, we can easily program it and regulate it like whenever, even when we're on holiday or like on break or something. And again, like agriculture is a very important like like a rising trend in today's society, and yeah, so this project is also contributing toward that and bringing sustainability to the future. So here are some of the measurable design parameters. So for the irrigation team, they needed to know what plants are growing there, because some trees and plants might use more water than others, and they have to um, account for that accordingly. So here's a list of plants that are growing in the native to Texas prairie, and we also need to know about like the water use and everything. So for every watering cycle, it depends on the time of the year, but during the summer, it's going to require around 200 gallons of water per week, and during the winter, it's going to require around 100 gallons per week. Ms. Deinhammer also told us that she prefers not to like dig into the soil to install the system because that'll just make maintenance hard. And we also need to know that a full cistern is approximately 300 gallons. So it'll last us between like 1.5 to 3 cycles depending on the time of the year. Okay, so some of the design parameters for water collection. So water collection, they knew that like monthly average precipitation is between 1.9 inches at the lowest and 5.15 inches at most. So again, like I said before, the nearest downspout redirects rainfall over a 15,000 square foot roof, and all the water is going to be coming down that downspout over time. So our solution, like if we're going to harvest rainwater, it needed to let the natural water or the runoff, like it should not disrupt the natural runoff. And the fourth point I have there, which is hidden by the picture, I'm sorry, I was working on this on PowerPoint, and when I moved it over to my iPad, I had some issues. But the fourth one basically states that our cistern is guaranteed to be full at least once a month. So at the minimum, just from rainfall, because like at the minimum, we'll get 1.9 inches per month, and over a 15,000 square foot roof, that's still like over 1,000 gallons. And so our cistern is guaranteed to be full at least once every month, and that'll last us again, like I said, depending on the time of the year, approximately 1.5 to 3 cycles, and including the rainfall. If there's rainfall during certain months, we have to also account for the rain that falls on the 2,000 square foot piece of land we have, and that is more than enough to water the plants itself. And so we could save the water during when it's raining and use that in a later date. And so our system will be sustainable just using rainwater, but just in case we go for a long time without rain, we just need to have city waters backup according to this Deinhammer specification. And lastly, we have measurable design parameters for the off-grid team. And they need to provide enough energy to power irrigation system and water collection system. And after further research, we discovered that it's 112 watts to power both of those systems combined. And obviously, they need to store extra energy for when it's not sunny or when during the nighttime, and during the winter months there's more like cloud cover than normal, all that stuff. Okay, so as part of part 3, we did speak to a qualified representative of rainwater collection and irrigation systems, Mr. Gary. And after talking to him, we took some notes and we revised some of our parameters. So for irrigation, Mr. Gary suggested that a point source irrigation is generally good for the application we're trying to do. And this is because it's like durable and low maintenance. So these point source irrigation systems, they emit water at like a specific rate, and his suggestion was 5 gallons per minute, or his example rather, and he told us that after spacing them approximately 18 inches apart, it'll help you guys to uniformly distribute water. He also brought up the important point of what type of soil we have. In Texas, in this native prairie, we have clay soil, which we need to account for, and it takes longer for water to dissipate within clay soil. So Mr. Gary told us that whatever emitter or like water source we're using, we need to like go below, like way below the specification they state, to make sure like the water has enough time to spread out evenly. So some of the revised design parameters for water collection include, he was talking about filters. Mr. Gary was talking about filters, and so he told us that like a screen filter at the entry point will prevent like any large particles, and first stage flush filter will make it better because it'll then get rid of all the sediment and like small particles before it goes into the cistern. And again, he reiterated that the solution we make should not interfere with the natural water runoff, which is again very important because we don't want floods. And here are the revised design parameters for off-grid. So he told us that like cloud cover, one of the most important points he told us was that cloud cover affects like solar panels way more than we may think. So we need to schedule irrigation and um, battery storage accordingly. So yeah. Okay. And for part 4, this is about the design process and analysis. And here I'm just going to talk about the solution that we've come up with for all 3 of our teams. Okay, for irrigation, we decided to use drip line irrigation, which is a method of irrigation which uses flexible tubing that goes over the soil. So we meet Ms. Steinheimer's preference of not having to dig underground. And so basically, how this works is the water is regulated from the cistern at a 25 psi pressure and is fed through multiple point source emitters, which are spaced apart to serve the plants with water. And so yeah, that's our solution, and this meets and satisfies all our constraints. So for water collection, we have like a little tray within the storm drain to collect and pump out water. And we also have an overflow cutout because again, we don't want to disrupt the natural water flow. And I actually have some pictures that I would like to show of this. So this is like a render I made in SolidWorks, and so you can see that like large rectangular hole there, and once the water fills up to sorry, one second. Yeah, once the water fills up to the bottom of this rectangular hole, it'll start overflowing through, and it might look like the hole is unnecessarily large, but the hole is actually designed to match the flow rate of the downspout and all the water that can potentially go in. So even during like the worst case scenario where we have like pretty much like extreme rains, we will be safe because like this cutout can carry as much water out as the downspout can carry. And as you can see, there's a PVC pipe leading out going into the cistern. And again, this is a rough model of the cistern, and the water will just fall back into the cistern from this. So again, the water is going to fall into this like collection unit, which is made of sheet metal, and will go into the cistern for storage. And there will also be, it's important to note that there will be a filter that will be located above this in order to filter out any unwanted particles, and the pump will be inside. And finally, for off-grid, we are using solar panels mounted on the roof at a specific angle, which is most efficient during both summer and winter. So the angle is approximately 28.4 degrees, and we're mounting this using like steel square tubes and essentially just welding like a frame for it and bolting it down into the roof. And yeah, so that is my reflection. Oh, one more thing I forgot to mention. So all our solutions, I'm sure you know this, but we started from 3 design sketches, narrowed it down to 2 sketch models, and then finalized one idea for our mock-ups, which we are yet to make. Thank you.